Alright, this is going to be the archived version of what we did in class, the in-class lecture where we talked about the actual pendulum. Now we're going to go through the same kind of thing we did before. We're going to solve the pendulum system by writing down the restoring force or torque, putting it into Newton's second law, generating a differential equation, and solving that differential equation. So let's first start by drawing what a pendulum is. A pendulum, the simple pendulum anyway, is some sort of string, and on the end is a heavy weight. String has length L and the weight has mass M. The heavy weight on the end of a simple pendulum is called the pendulum bob. Hi Bob, how you doing? All right, so if we pull Bob to the side, an angle theta, he will wind up over here. And we've said before that the magic of the pendulum is that Bob rises up and that gives him potential energy, which allows him to swing. But if we want to really understand this, we're going to need to analyze the free body diagram for when Bob has been pulled to the side. And that looks something like this. So there's a bit of a mismatch between these two forces. And this is one of these situations where it's good to analyze this in a tilted coordinate system because tension is going to be opposed by one of the components of weight, but the other component of weight is going to be going this way. It's going to provide our restoring force. So if we go ahead and componentize it, the diagram is going to look like this. mg cos theta here, and mg sine theta is the restoring force. So we can conclude that the restoring force is equal to minus mg sine of whatever angle we pull it to the side. Now, since we have our angle theta is the variable here, I think that this is going to tell us that we're going to be headed into torque land. So we'll also write that our restoring torque is equal to the restoring force, but times the lever arm, which is L, the distance from the pivot point that force is acting. I'm going to slip the L in the middle so that sine theta is the last thing in the line. Okay, so if we were doing this, and we are, we would write down Newton's second law in its rotational form. That is that the net torque is equal to I times alpha. We would substitute in this torque for the net torque, since at that moment that's the one that's doing the job, minus mgl sine theta equals, now I for a point mass is simply ml squared, and alpha is d squared theta dt squared. And if we clean this up, we're going to get our differential equation. First of all, the masses cancel. This L cancels one of those two. We can get the other last L to come underneath, and we're going to wind up with minus g over L sine theta equals d squared theta dt squared. And although this looks a lot like the differential equation we got before, it is not. This one is very, very difficult to solve. You see, last time, here I'll put the other one underneath. Last time we had minus k over m, well, actually 2 times ago, times x equal d squared x dt squared. Last time we had another one that had thetas in it. I should have used that one. And the idea is that we're asking the question when we guess our solution. We're asking, which function can I take 2 derivatives of and get back the same function and a minus sign? And the answer is just resoundingly sine or cosine. That's how they behave. They are their own grandpa. Take 2 derivatives, you get the function back. Take one, you get the other function. This doesn't work that way. This says, what function can you take 2 derivatives of and you get back sine of the original function? So if we put sine in here, we'd have sine of sine in here, and that's a little too much. And we should have known this wasn't going to work, because one of the rules about simple harmonic motion, the kind that you can easily solve, is that it has to have a linear restoring force. The force as a function of our variable has to be linear, and there's a line for you. All right, it doesn't matter what the angle is, but sine doesn't behave like that. Sine has humps and bumps. So sine, this is a linear, and this is sine, and they're different from each other. But if you look closely at this area, like right in between, say, here and here, those two are right on top of each other. So at the very least, for some of the initial part, I mean, that looks like it's almost all the way to pi over 2 radians. They look like they overlap and could be pretty much the same. So let's make an assumption. Let's limit ourselves to small thetas. Okay, that's supposed to be a theta. Now, what happens if you limit yourself to small thetas? Well, Taylor's theorem says that any function can be represented as a polynomial, an infinite polynomial, and the function that represents sine is theta minus theta cubed over 3 factorial plus theta to the fifth over 5 factorial, etc., etc., etc. But if for small theta, that means that theta cubed is way less than theta. And way less than theta, even divided by something, means the second term is way smaller than the first term. And the third term is way, way, way smaller than theta. So if this is true, if we limit ourselves to small thetas, then sine of theta, according to Taylor's expansion, can be approximated pretty well by just theta. And under those conditions, this differential equation turns into minus g over L theta equals d squared theta dt squared. And now it does look exactly like this one over there. Now, normally what we would do is we would write down our guessed solution with our two parameters in it, a for the amplitude, omega for the timing factor, how quickly you go through all the different phases of the motion, and we would take derivatives and we'd put it back in, but we know exactly what's going to happen. The two derivatives on this side are going to pop out a minus sign, and they're going to pop out omega squared. And this side is going to have just the function in it, which cancels everything from that side that we don't care about, but the minus sign goes away. That's what's going to happen. So instead of doing all the stuff, I could just, allude to that I've done before. And if you don't believe me, you can do it yourself. It works 100%. So that means that omega for this situation is the square root of g over L. We go around our phase diagram at this angular velocity. Something springy divided by something massy. In this case, springy is the gravity that is pulling things back. Something massy is pretty much the lever arm or moment of inertia of this thing. The mass has canceled top and bottom. That's what makes pendulums really neat, because they work the same only depending on length and not depending on mass. Galileo noticed this. He was in the cathedral or attending church, and he noticed that whether the lamps were full of oil or almost empty of oil, they had the same period if they hung on the same length of chain. Now, one more thing you can do is that the period of the motion, the actual time it takes to go around or to go back and forth for a pendulum, to swing away and come back to your starting point, is going to be 2 pi divided by this angular frequency. So that means 2 pi times the square root, and you flip these things over, L over G. And this is actually the equation that Galileo came up with when he was studying pendulums, and he did not use calculus. Calculus had not been invented. He observed this and measured it and came up with the idea that this must be the relationship by changing the length of the pendulum and seeing how it worked. So that's the main thing you do with omega, is you use it to find the period. So a little side note here, omega can help you find the frequency, because that would be omega divided by 2 pi. Frequency is how many times per second something happens. And then period is equal to 1 over the frequency. How many seconds does one thing take? And of course that would be 2 pi over omega. So omega, once you get it, it gives you these time-related things immediately. So that's what we know about the pendulum. You could write down the angular velocity, the angular position, and the angular acceleration as a function of time. Figure out what's going on at any time in the future. You own this thing, okay? All right, that's enough. We have one more of these to do.